Hello, everybody. Welcome to our virtual 3D showroom open day from Konica Minolta in Sydney. Hello to all our friends in Victoria. Unfortunately, we can't be with you in person, so this is going to be an online event, and feel free to enjoy. So today we're going to be discussing a series of technologies that we at Konica Minolta provide to our customers for additive manufacturing or 3D printing. My name is Wojtek. I'm the digital 3D engineer, applications engineer at Konica in Sydney, and I look after across these applications and CAD work and so forth. So feel free to ask any questions you have about anything related to it or how it works. So we'll start with a quick presentation to outline what we have at Konica, what we offer. So welcome to our virtual showroom. We'll be showing you guys a series of technologies live on the video that we have in the showroom here. But before we do that, we're actually going to discuss a few of the larger technologies that we don't have in stock. Because we do deal a lot with industrial applications, we have a lot of machines that people may not be aware of that are used for making end-use parts in both metal and plastic. So we'll cover those first to give people a really broad scope and really introduce people to the idea that this technology is a very valuable manufacturing technology, not just a prototyping technology or a hobbyist technology. So let's at first have a look at these. We've got Markforged Metal X, which is an end-use metal manufacturing print system that we have. And we also have a range of 3D systems machines. As some of you might not know, Konica Minolta is an exclusive partner of Markforged and 3D Systems in Australia. And we provide the equipment manufactured by those vendors. 3D Systems is actually the company that originally invented 3D printing back in the 80s. So they've got a very, very strong and large portfolio of incredible 3D printing machines. Markforged is a newer partner, but has been a very fast-growing, very quickly overtaking the market because of the quality of the parts that they provide. And you'll have a look at those in a minute. We've also got a range of specialized software solutions for scanning and reverse engineering and CAD work, as well as medical imaging, primarily from 3D Systems. So at first, we'll have a look at this Metal X technology. I'll just talk over the top of these videos to give you an idea of how it works. So you can see everything starts with a CAD model. You obviously have to model your part up somewhere. And over here, you can see the parts being put into the slicing software of Markforged, which is called IGA. It's used to slice and prepare all their parts for printing. And you can see this is the budget way of printing metal. They're still end-use metal components. They're not delaminating. They're not hobbies. They are end-use metals. You've got metals like Inconel, stainless steel, tool steel, and copper. Currently, it's the most stable 3D printing system used for printing copper in the world. So you can see the parts are printed. Then they're put into a wash station. They're cycled in the wash fluid for however long they need to be, depending on the geometry and size of the part. And once the part's washed out, take it out, and you put it into a sintering oven that is used for heat treatment. So that's a sintering oven that you get in the actual system itself. You can't just put it into any sintering oven. It's a very precise system that's controlled. The heat curve is controlled by the software. And then the part comes out. It has a little bit of shrinkage to it. Then you remove it from the supports, and it's an end-use metal component. You can machine those parts. You can use them straight out of the printer, depending on what you need. But it is a legitimate end-use metal part. So that is a Markforged printing solution. That is on the lower end of the price spectrum. I'll show you the VMP solution, which is the other end of the price spectrum for printing metal. So this system here is a laser fused powder system. Sorry about the lack of sound on the interviews, but essentially all these guys are just talking about is how good these machines are, which is very true. This is a much larger system. It uses metal powders. It has a broader range of materials than Markforged and prints a much higher level of detail. Unlike Markforged, these parts can be used for things like human implants in the medical industry. They can also do things like internal features, fine features. Currently, titanium and aluminium is available. and the build bed on these machines is significantly bigger. I think the largest printer goes up to about a 0.5 meter cubed, more or less. As you can see, you can do things like lattice features, internal features, light weighting. It's a different method of printing to the Mark Forged, and it's a much different price range. So where for Mark Forged, you expect to pay maybe in a range of about 300,000 for the system setup. For this particular system, you're looking in excess of about $1 million. And the machine is much bigger, but it does have its application in the market. Things like aerospace design, automotive design, for things for, there's been parts that have been rated for aerospace that now come off these systems. It's a different beast and a different price range. Next system that we have is SLA, and this is traditionally associated with prototyping because the way it works is it's essentially a resin bath where the laser, a very precise laser from above, fuses the parts layer by layer into a solid. And the parts they're not end-use components. They're not the strongest of plastics, but they are very, very high definition. And you can see in this video, this is a company that what they do is they investment cast aluminium components. So to print parts that big would not be viable. But what they do is they actually 3D print the pattern for the investment casting out of a resin that has a very good burnout rate. What that means is once the metal is poured into the mold that contains the pattern, it doesn't leave a lot of ash and it gives you a very clean casting. And by doing that, what they're doing is they're taking advantage of the cheap, I guess, the cost effectiveness of pouring metal rather than printing metal, because poured castings are much, much cheaper, as you probably know, rather than printed parts. But they're taking a huge amount of manpower and labor out of the process of getting there. Traditionally, they would have to make injection molded tools to make these patterns and shoot them out of wax and then melt that wax out. Whereas now they can just print them, as you can see here, put them together into larger components, and then put them in either a sandbox or a ceramic and get the advantage of poured metal. So the microstructure of the actual material is traditional. So you don't have the problem of getting parts certified as being printed. They're still cast and they're still the way that they have always been made, but you're not reverting to any kind of subtractive manufacturing to make them. You're not wasting anything. You're getting very precise parts with virtually zero waste right over here. I think this particular company saved something like 95% on their pattern making just by switching over to 3D printing these patterns. When we go through our samples in a few minutes, I will actually show you a sample of this particular technology. It's called Quick Cast. And as you can see, it prints with a lattice on the inside of the part as well. So it has a nice solid skin, but the inside is in solid resin. It's just a very lightweight lattice that burns out very easily, but holds everything together with a lot of strength and rigidity and dimensional tolerance. So we'll hop over to one more video. And this is SLS. SLS stands for selective laser sintering. This is very similar to the technology you just saw for printing metal, except it prints a range of nylon powders. It also prints a TPU, which is a soft material. Now, SLS, once again, these machines are from the larger machine range, so they are the size of a small vehicle, and they are obviously very expensive. For SLS, you're looking in a range of about $500,000 plus. But they do parts that are very large and they're very, very reliable and also very fast. So you'll notice throughout the video, there's footage of a cube of powder. And the way that works is the machine starts with no powder at all. And there's a little gantry that deposits a layer of laser sinterable powder on the bed. And then the laser goes along and fuses the cross-sectional layers of the model together. And then the gantry comes back and deposits another layer of powder, and then the laser repeats and fuses that powder to the layer below and keeps going until that whole cube is nice and full. Then you take that whole cube out of the printer, take off the plastic, and then physically break all that powder off. The wonderful thing is you can take all that powder and suck it back into the machine and recycle it. You can change the recycling rates depending on what properties of material you want, and then run jobs all over again. Because it's powder, it's self-supporting. You don't have the the hassle of setting up support structures. As some of you might be familiar with 3D printing, you always need supports to support the part. So over here, because the powder is, it's a single material, powder self-supports the model around it. You just have to give it a little bit of time to cool down. And as you can see here, there's a whole series of nylons. You can see the parts, the machine's been out for about 2.5 years now. It's a very, very reliable, I guess, tried and proven technology that is very popular in the medical market for doing things like inserts for shoes, your orthotic devices, splints, as well as plastic parts for automotive and other such applications. They're very strong. You've got things like fire retardant and other kind of properties that are very valuable to industry. All right. So now we'll have a quick look at what we actually have in our showroom. Before we actually switch to video, I'll just take you through a few of the key features so that you know what you're going to see that's coming up. So the three technologies we do have here are the Markforged X7 printers, the 3D Systems DLP, and the Project 2500. We're mainly going to focus on the Markforged and the DLP. We might just mention the Project very quickly, but the two key ones, I think, the most valuable ones and popular ones are definitely the Figure 4 and the Markforged. So firstly, just quickly on the project that we have at the back, it's a technology called MJP, which stands for multi-jet printing. It is used primarily for prototyping plastic parts that are roughly an A4 size bed, about 200 millimeters high. And you can use it to prototype injection moldings that very closely resemble in dimension and size and shape what you're going to get when you get out of the mold. So before you pay for an $80,000 tool, you can obviously pre-visualize what you're going to get and make any changes, which is very valuable. It does a series of about maybe 14 materials at the moment. Some of them are high temperature, so you can do things like rapid tools. It does a very high level of detail. The printer has a version of it that is the workhorse for the jewelry industry. So a great percentage of jewelers in Australia have been running this system for years. It prints a very high detail wax that has a very good melt out point. So I think any jewelry for the last 15 years that anyone's bought has been 3D printed, not carved. Wonderful thing is also it's got a wax support that you can melt out, so you don't have any of the sanding or ripping out material manually. It's just a very nice cleanup with very minimal effort. And the software you get for it is very, very easy to use and very powerful. So you can put a whole bunch of different files in there without thinking about it too much. It just what it does what it's supposed to do. So that's one of the technologies we have. Second one, which is probably our most cost-effective printer. It also happens to be the fastest printer on the market at the moment. It's 3D Systems Figure 4. This is our DLP technology, and the way it works is it has a projector at the bottom of the printer, and I will show you this live in a few minutes, that shoots a beam of light up into a tray full of material that has a clear window at the bottom of it. And the bed then rises out of that resin and fuses the part layer by layer as it flashes UV light from below. And what that means is whether you have 1 part or 10 parts on the bed, the print speed is going to be the same. There's actually a resin on there at the moment that'll print at about 100 millimeters per hour, which is very, very quick. But there is a huge variety of end-use resins as well. The machine's primarily used for replacing small injection molded components where a customer might need, anywhere between 1 to a couple of thousand parts, rather than 15 or 20,000 plus, where they have to mold and tool up, which gives them a huge cost saving, because obviously you can do infinite design iterations, design changes, and many of the materials are essentially as good as injection molded plastic. It also has materials for medical applications that are sterilizable, so you can do things like surgical guides. It has a jewelry wax and a whole series of others that we can offer. It's also very low cost. Resin is very cheap, and to get up and running with a new job, the change out of the material is very painless and quick. Plus, it's a very small printer. It can sit in your bedroom or your office. There's no noise, no fumes. And yeah, once again, it's very cost effective as well. It's probably the cheapest one we have in our range. Last but not least is the Markforged technology. You'll see the X7 machines, which are the sort of the bee's knees for Markforged. It's the large industrial model. It's traditionally, I guess, an FDM based printer, so it does extrude essentially a plastic pasta, but that plastic pasta is anything but pasta. It is a plastic nylon that is filled with chopped carbon fiber. That is a material called onyx, and it is the base printing material for Mark Forge printers. There is a secondary head in the machine that then can, if you like, reinforce the part with a continuous fiber. And that fiber could be either carbon fiber, Kevlar, fiberglass, or high temperature fiberglass, depending on the application of the part. So this machine is designed for very, very high-end prototyping that replicates very closely structural strength of parts that you might need. A lot of customers haven't been able to prototype off cheaper PLA machines because the parts break. They don't replicate the strength of things like glass molded glass with nylon injection moldings very well. This one does. It's very repeatable. It has a very high dimensional tolerance, down to 50 micron. The printer itself includes a laser leveling bed, and yeah, obviously there. And at the end, you can either prototype with it or just go straight to end use parts. You know, it's completely capable of running end use components. We have quite a few customers who run their whole businesses just off this machine alone, and it's I guess the strength of molded plastics. The advantage of that, they're also machinable as well, and you can really redesign components and re-engineer them to make them better, and saving you a whole heap of money. Cost-wise, parts that would otherwise cost maybe $2,000-3,000 to machine, and I'll show you some of these on our sample cabinet in a few minutes, can be gotten down to about $150. The other wonderful thing about this printer is it has a digital online cloud software that makes your organization or your company's printers all nested into one software. You can see everything that you're doing. You can share assets between each other. So if you have a design team working in another country who is working on a project that you're also working on, you can very easily print exactly what they're printing on their end as reliably on your end if you both have the same printer and the same software. So I think without further ado, we might actually just dive straight into looking at these printers. But no one wants to see me. You all want to see the printers. So you can see we've got two X7s sitting here. Wonderful thing about these guys is, and I will go through all the features, is in the middle of a job, if you wish to add parts to the print, if you wish to add, say, things like threaded inserts, metal components into the plastic bits that you're printing, you can actually pause the job, take the printer out, the printer bed out, put your parts in, put your metal components inside the plastic parts, and as long as they don't stick out over the printing layer, put it back in and resume the job. It'll pick up exactly where it left off, which is really wonderful. That's something that FDM technology traditionally hasn't been able to do. Let's just wind back a little bit and we'll go through the features of how this printer actually works. So as I said, this is not a hot bed. There's no heated chamber here. It's a cold bed. The material, which is onyx, lives in a spool over there. I can actually show this to you very quickly. There is a dry box here. The material is very sensitive to moisture. So inside the dry box, you have a nice big spool of material, 800 cc's. You've got some silica bags over there. It's very important to keep this closed at all times. You've got about 15 minutes working time before the material starts to take in atmospheric moisture, at which point it can ruin the print job. So it's very sensitive. On that dry box, that material gets fed through a tube in the back, goes to here, into the motor that drives it forward. And the first time the material actually meets the atmosphere is when it comes out of the nozzle. So you've got two heads over here. There is the secondary fiber spool over there. It feeds carbon fiber or Kevlar or whatever you've chosen through the secondary tube to the secondary nozzle. Once the layer of onyx is completed, it'll engage the secondary nozzle and print the continuous fiber into the part wherever you want it to go. So it's really a very mechanically simple system, but you get what you pay for with these things. They're factory set. You don't have to assemble any of it together. So there's no 3D printed bits you have to print yourself in order to make the printer. This is why the machine is so good with repeatability, and we have a very high dimensional tolerance. So the parts that come off of this, as you'll see on the samples in a few minutes, the surface finish off them is quite incredible. So in order to start the print job, you launch your cloud software, and we'll show you a bit of that software as well. From that software, you set the print job up as you see fit, put it in the cloud. The printer then downloads the job, All you got to do to get the first layer started is put on a very subtle layer of glue on whatever part of the print bed you're going to put the part on, and then let it go. So the printer isn't the fastest printer, but it's extremely reliable. So where a lot of FDM jobs usually tend to fall over when the temperature has a problem or warp, this thing, you can leave it running. If the material runs out on a big part midway through the job, it's no problem at all. All you do is you come in, put in some new material, keep the job running. It'll pick up where it left off. You won't even know where it stopped. Big problem with FDM printing is you have to always budget the amount of material for the job you have to have and hope that you don't run out. That problem goes away with this technology over here. Like I said, there is a laser head inside the print head. So underneath, there is a very fine laser that measures the level and the Z-axis and the Z distance of the bed down to 1 micron. So leveling the bed, it auto levels before every single print. There's also a webcam in there that gives you feedback, live feedback of the job right under there. Right under there, so you can always see your bed. So if you're sitting there at 3 in the morning and you've got a tight deadline and you want to see if the printer back in the office is still chugging away, you can always have a look at that. So the software itself has very good tools for calculating the amount of time and the cost of the parts, and we'll have a look at that in a sec. So the kind of parts that you get from this machine, I'll show you right now. So, like I said before, this system is quite good for replacing components that may have originally been made out of machined aluminium because of the strength of the carbon fiber. If you design it and orient it properly in the printer, you'll find that you can actually replace a lot of originally machined components with plastic and still have them serve or outperform that purpose. Sometimes you can't, very often you can. This part is just a print of an aluminium hook that was originally being done by a company that has CNC chucks. So they've got drills that hang in here and a second drill that hangs in there. That's all this does. Right? It was machined out of a block of aluminium billet about yay big. So the part costs an obscene amount of money to machine, and they have probably about 30 or 40 of these hanging on the wall because they're a very large company. It does a lot of machining. The robot then comes along, takes the chuck off the hook, and loads it up in the CNC. So because they're always updating their chucks and they're always updating the drill sizes, they'd have to have a whole heap of these that needed to machine. So machining time would probably be about a week and a half. It's a 2-sided pass, and it was very expensive. So obviously the weight it had to carry was maybe about 15 kilos. So what we did was we redesigned it as a printed component. The same critical centers, diameters are still all there, but we redesigned it to be filled with fiberglass. Fiberglass is cheaper than carbon fiber, but very often it does a very similar job. So by putting this in that place, that still holds the same amount of weight, and the cost of this is about $150 versus three grand on that one. And the print time was about 3 days versus about a week and a half turnover for that part. And it does a wonderful job. So they could literally make this customized to what they need to do, lay them up on the wall and pump them out as they need them at a significantly lower price point. So that's something like that. Because of the wonderful bed size on that, things like drones, that's a single part. If you're clever, like us, you can design internal features. It's a bit hard to see, but if you look in there, right, in there, and in here, and I'll show this to you on the metal parts in a moment. If you design things with a diamond roof like that, if that angle is 47 degrees or more, there actually won't be any support material that's deposited to hold up that roof. So because you've done that over here, you now print the whole drone in one part, and all the conduits for the cables and all the systems in that drone can be printed in there with no support. You just put this thing together, put a lid on it, and off you go. Put your motors in and all your electronics if you choose. So you can reinforce this with fiber if you want extra strength. Kevlar is particularly good because it has memory and it bounces back as well. So large parts are no problem. You've got components like this. Another big application is jigs and fixtures because the definition of this is down to 50 micron. FDM once again has never really been a very good dimensionally friendly technology to print. Not so with this one. So if you are curious about how the continuous fiber works, over here you can see a brake lever that's just been printed in onyx, right? So you can see the surface finish is quite incredible, right? But there's no internal, I guess, stiffening with continuous fiber. So you can see it looks beautiful, still a little bit soft, right? So if you wanted to give this part a significant amount of strength, you would then deposit a whole concentric series of fibers over here that's continuous, and that could either be, this is carbon fiber, so it's a little bit hard to see, but it's there. You could also do this out of fiberglass or Kevlar, high temperature fiberglass, and you can see now that's very difficult to bend. So this can be used as an end-use component, and this is exactly why something like this could be stiffened and printed out as something like that. It's got that strength of aluminium, and it does the job. So once again, big parts like this used for industrial automation, no problem. Surface finish is pretty impeccable. That's what the finish looks like off the bed, nice and flat, very smooth. And we've done a lot of testing of parts like this with automation companies for packaging, and many of them are actually outperforming the steel components because a lot of the steel parts don't need to be steel. They can actually be made out of nylon. Nylon is nice and smooth, nice and light, keeps the machine going. You've got other options for electronics manufacturing. There's an ESD nylon. What that does is it's got electrostatic discharge. So if you've got electronic boards, you're assembling electronic products where you need to hold the board, or you actually want to print a housing for something with a piece of electronic hardware in it, this material takes that static load and makes sure your boards don't fry up. So once again, same as this kind of material, but it's got a little bit of extra carbon added in there to give it a properly rated electrostatic dissipation over the whole part, which is very cool if you are dealing in electronics. You can print electronic boards in there. So something really nice that you can do is you can put a chip or an RFID tag, for example, into the actual component and then print over the top and encapsulate it to make it waterproof as well. That's a nice way of using it. And the feature I was telling you guys about before, about putting metal components in the print, we've done that right here. So you can see that's been printed. It's got metal rods and inserts that have been placed into it. Now, if we wanted to continue, we could actually print over the top of that, house that in there to give it incredible strength. You'd never even know it's in there, but you can do that during the actual print job, which is great. So moving on to the Metal X components, this is the machine that we don't have here, but as you saw in the video, size-wise, the printer itself is very similar to that. You just get the extra wash station and the oven. And the metal parts you get off that look just like this. So they're legit metal parts. You can print a lattice infill inside, which is actually a wonderful thing because where traditionally you would make parts out of billet, now you can make the same part with a hollow internal volume and a lattice and take a huge amount of weight out of it. So this takes about 2/3 of the weight out of a part like this. So one cool thing you can really do is do material replacement for parts. So you've got parts that could originally be made out of aluminium, where you can actually now replace them with steel and make that steel lighter and have a significant more amount of strength and replace the alley, but be steel. So a whole world of design opportunity can be open. So anything like things that are just like cast tools, obviously you can customize your tools. You can see there is a little bit of stepping, and that is just the nature of the printer. You can machine that off, you can rumble that off, polish it off. It's legitimate metal. Once again, the only printer in the world that does stable copper printing. Copper is very hard to print in powder because it's very conductive. So it's very hard to control the laser. So things for welding, components that need a high amount of conductivity, things for dissipating heat, like heat sinks as well with very organic shapes, we can all do off this. The parts themselves, this is the part you actually saw in the video. Right? So you can see what I was saying before about the diamond cross section. By having that diamond, there was no support material deposited inside there or there. So this part comes out and the internal channels are empty and ready. So for things like tooling inserts for injection molds, wonderful stuff, because you can print conformal cooling, helixes, and all sorts of shapes inside the actual part itself without having to worry about ripping out all that metal support. The parts themselves, you can see that that's a part that hasn't had the support taken out. The support itself is metal right there. There's a very fine layer of ceramic in between the part and the support. If I was going to whack this with a hammer, all of that funny area would crack out, the base would crack off, we'd be left with a wonderful end-use metal part. So that's what that looks like. I guess we'll move on to the next technology. Actually, no, before we move to the next technology, I think we'll show you the IGA software of how the parts are loaded into this system. I'll show you how quick and easy that is. So I'll look over here. All right, hopefully everybody can see that. This is the IGA software that you get with Markforged, and it controls all Markforged printers. So whether you have a metal, whether you have an X7 or maybe one of the smaller ones, this software will control the parts and the printing for any of the software in your system. So you can see, let's just have a quick look at, say, the drone part that we saw. Right over here. We'll pick a smaller part so it's easier to manipulate. So you can see you load up the file, which has to be STL. It has to be an STL format file. On the left, you have the things like the part dimensions, the outer dimensions, the print time. Currently, this part only takes 13 minutes to print. That's the mass and the plastic volume. I haven't set any fiber and the cost of the material in US dollars. So it's very cheap, tiny little part. So what's that? That's 2 cents US to print that part. So you can set up. Should actually get back for a second. Pick something from the library that's that I can access. Here we go. All right, this one I can play with. All right. So let's have a look at the lever. You pick on the right here. You've got all the basic settings for the print. So you got material. Any of the available materials for Markforged are there. Obviously, I can't pick copper because the printer that I'm going to be using is an X7, which doesn't do metal. But this is the whole different range of materials available at the moment. There's more coming, titanium and aluminium included. Over here, if you want to do reinforcement materials, so if you want to put a secondary continuous fiber inside that handle, then over here you can pick the one that you want. So we'll stick with carbon fiber. And here's the type of printer that you want. So you can see if I was going to pick metal, then it won't let me use any of the previous materials. It'll just revert back to one of those, right? So I'm just going to go back to the X7. And there's a whole series of printers. There's an X3, X5, X7, and there's smaller baby desktop versions. We have the X7, so that's the one we're going to stick with. There's small differences between those printers with the material availability and size, but otherwise they all do a great job. So we'll set the reinforcement to carbon fiber and go to settings. When you do print in fiber, in carbon fiber, you're locked to 0.125 layer height. If we're going to go back and put none, we could then pick different layer heights right down to 50 microns. But because we're using fiber, this is all part of really understanding the technology and where you want detail and where you want strength, and then orienting that part accordingly to take advantage of all those things. That's very important to understand that, because you can really go far with parts of this system if you do understand how that works. So we've got things like infill, fill density, reinforcement. So I'll just quickly show you a secondary part of this. Once you calculate the part, you can see it'll paths. That's the actual tool paths for all of your gearheads. That's the G code like you would have in a CNC machine. That's generated that, and now you can see that's given us a print time, the fiber, the plastic volume, and you can go to internal view. Internally, it'll show you how the fiber looks like. Right, see the blue stuff is the carbon fiber where it sits. You can pick any one of these groups over here. You can set up your own groups where you want fiber to go. So over here, if we wanted to add fiber, we'd hit use fiber. All of a sudden, it'll add fiber to that. And then we can see over here, The blue is the carbon fiber. You can go to 2D. In a 2D view, you can then scroll to any layer that you like, and you can see that's where it'll deposit a solid onyx, that's where it'll deposit fiber, and you can make all those changes over here accordingly. And it's an infinite amount of combination depending on how much strength you want to have in your part. A lot of the time, you don't need to bang the part full of carbon fiber. You can just put in a few layers. It'll do the job just fine, but that comes with experience of using the system. Once you're all done, you save your part, save all the changes, and it'll update. You can then go to print. That sends that part to a secondary part of the software that shows you the print bed. And over here, as long as other parts have the same layer height, they can either be with or without fiber, but as long as they're 0.125 mil, you can bang this bed full of parts and then send it to the printer. You can either export it as a print project or send it to the Sydney printer over here or any of the other ones you might have put up on your network. And that's really all there is to it. Once it's in the queue, it's ready to go. So without further ado, I think we might hop back onto the figure 4 technology. So come with me and have a quick look at this. This is the figure 4. That's the DLP printer. Like I said, I can't open this at the moment because it's running and printing a job, but there is a projector inside there that is projecting very, very high definition light at the bottom of this material tray. That material tray is full of resin. Resin comes in bottles like this. It's about a liter, it's about a kilo. And then you just top it up to a certain point in the tray. To change that out, all you have to do, you've got little garages like you can see over there. The garages just sit in little plastic trays. They've all got different materials in them. If I want to run another job where that has different material properties, different materials, I just pop that out, take that tray out, put it in a garage, put a new one in, lock it up and keep going. Because it's UV light sensitive, a lot of people are always curious about why this thing is orange. That's actually a UV filter. If we took that orange away, that would fuse all our material solid very quickly. So once the job goes in, it then starts to raise out of the bed layer by layer by layer. And then that's a magnetic bed. So once the part is finished, like I said, it's a very fast printer. So this particular job is only 54 more minutes. The whole job is about an hour and a half. Once that's finished, I can just pull that out, pull those parts off the bed, give them a quick wash in some isopropyl alcohol to get rid of all the residual resin, and then to a final cure of them in a UV box. So there is actually a scanner underneath here to make sure people know what they've put in there before they press play. There are little QR codes on the material that you can see here. Once you set the job to print, you then scan your bottle because it then tells the printer that you have confirmed what material you've put in that tray. I think the most common mistake that customers make this is telling the printer they've got one kind of material in the tray and then pouring in something else and not noticing that they've done it. If you do that, you can damage your printer. So this has just got a series of fail-safes that protect you from damaging your equipment. And once you've done that, like I said, this machine is very fast. So it's all about fast material change, fast part removal. The moment you take that bed out, you can put your second bed in and print another batch immediately. You just hit reprint on the job if you're running multiple jobs. The other cool thing you can do is you can hang jobs one underneath another. So if you've got small parts, you don't have to just run one set of parts on the bed. You can actually hang as many as you can pull in. The bed is quite small. The reason for that is because it's a light-based system. So it has to focus that light onto a smaller area. It is traditionally jewelry and dental technology, but where it is a small area, it's a very big height. It does have a big brother, and the big brother has about a half a meter worth of height, bed height, that he can fill full of parts. So sometimes you can get up to a couple of thousand parts and run it on a 12-hour build overnight, come in the morning, and you'll have a nice long bit of parts hanging off your bed. Then you just snap them out and they're finished. So the whole idea behind this system is speed and low cost. The resins are very cheap. So something like this, which is about a kilo, if you're doing small components, you might be able to get up to 1,000 parts out of that little bottle, which is quite incredible. And that means that the cost of a part might be 20, 30 cents, where, originally, if you were going to mold that part, you'd have to shell out maybe $20,000 for a tool and then make 50,000 parts to get that tool discount and keep them in a tub. but you might only need 100 or 1,000. So the tool cost and all of the shipping costs and everything involved in that process would pay more than enough for a whole printer, all the material you need, and then you're free to develop as many products as you want, and develop new products and make design changes and so forth. So if the material is applicable and it meets structural specifications, then there's no reason not to do it that way. We'll have a quick look at the samples that come off the printer. So you can see it's very, very, very high detail. And I'll show you, these have digital textures on them. They're going to be a little bit hard to see, but look very carefully. It goes down to about 10 micron, and you can really, really make that stuff is not an error. That is actual digital textures, and it's probably one of it is over there. So you can see it's a little. It's actually off a gear stick, right? You can see that nice vinyl texture over there. There are support towers that bind this to the bed. You can just snap them off. You don't know how it's been printed. Very, very strong part as well. So parts like this, polypropylene like, this is a little electrical housing. You can see, look at that. So that actually has legitimate strength. It is just like the molded component. Obviously, it has a different microstructure of material, but it's still quite strong. What I was saying about doing little parts, I was actually thinking of this little guy that's like a little earbud, and that's a legitimate plastic part, just like a molding. This is a very similar material. This gray material actually prints at 100 millimeters per hour. So you can see things like knobs. So if you might only need one of these things for your kitchen, or you might have a business where you make kitchens or any other device that needs little knobs. Why would you spend $20,000 to tool that up and shoot it and then, ship it from somewhere where you can just print one or print five, however many you need? Other materials, this is a HT300. And what that does is it's a high temperature 300 resin where you can print parts that need to withstand up to 300 degrees Celsius. So things like rapid tooling, little, if you want to actually physically mold a small component, you can actually print the tool block, the tooling set out of this. Anything that needs very hot air, hot liquid circulation, things like that, this is exactly what it'll do. Obviously, the parts are limited in size. You can chop them, glue them back together if you need to, but if you can fit it on that bed and it's a small part, then that's exactly what it'll do. There's also a series of rubbers. So this is a little scaled down version of little automotive component. That's a rubber 10. So that's a little bit of a stiff rubber that's very hard, very, very strong. This one obviously is used for moving air, but you can use it for wherever you use rubbers, handles, anything like that. Customize it at a very high level of detail. Obviously, you can put logos, names, serial numbers, things that need serializing and mass customization are very good 3D printed because you can change them on every single part, make them different. There's a wonderful rubber 65A. Check this out. See that? That's super cool. So that's a 65A kind of end use rubber. So there's a lot of customers we have that purchase a Mark Forged machine and they want to complement the hard parts they get off that with soft parts. So things like seals, custom seals that go around fiddly areas, things that might be difficult to mold. Very often they'll double down and get one of these to print the softer materials on, harder materials on that one. So that's the kind of stuff you get off the Figure 4. Now, just while we're here, I thought I'll take a moment to acknowledge the quick casting pattern. This is the one that you saw in the video. So you can see that internal lattice in there. That makes it a very lightweight but strong component, but this is designed to be destroyed inside a casting. You pour your metal in, burn it all out, right? So that's off the SLA system. Once again, these machines are bigger, they're more expensive, but you get this incredible quality. And just to show you the dimensional, the quality you get from these industrial machines, that's an SLS component printed out of sintered nylon powder, right? So you can see it's a little bit rougher. That's an SLA component printed off a resin. You can see how beautifully that fits, right? These are straight from the machine. They haven't even been sanded. They've just been pulled out and they meet exactly. So for things with SLS, you could actually do an end-use part out of this. With SLA, not so much, but you can see there is almost no dimensional problems with those two things coming together. So the consistency of this is mind-blowing. Things with SLS, like I said, these are drone components. So you can dye these a certain color. You can put internal features in there, printed all as one part. These are end-use nylons. You can get glass-filled nylons. You can get softer TPU, all sorts of things like that. So that's the range of stuff that we have here. I guess I could talk about this all day. If there are any questions, give us a call. Konica Minolta, that's us. My name is Wojciech. If you want to email me, it's woj@konicaminolta.com.au. I'm happy to talk to anyone about anything relating to this technology because I love it so dearly. But we're happy to answer any questions. I guess our big bread and butter over here is analyzing your business and looking for return on investment and really kind of cutting through and seeing if this technology is applicable to you. We've found that most people that make anything, whether it be the end bits for shoelaces or phones or toasters or anything like that, usually have a step in their process where this technology will save them money and it will save them time. It'll all lead to upskilling in your business. It'll all lead to a new understanding for new technology and kind of keeping up with places like America and Europe. With what's happened in the last 2 years, especially with China, and loss of IP, we found that we can't really rely on other people as much as we have been. And I think all of this, having all these things nice and close really does help us control our own manufacturing, control our own IP, and I guess control what we're making and helps build the Australian industry. So that's what we do here. Happy to talk to anyone. And thank you very much.
Giving shape to ideas. Konica Minolta.